This lesson is 4.8. This is going to be analyzing graphs of polynomial functions. Okay, so there's a lot of concepts that we've learned in this chapter that we're going to kind of put all together in this lesson, which is the relationship between zeros, solutions, x-intercepts, and factors. So if you have a polynomial, which is represented by this, then we know the following. If k is a zero of the function, then x minus k is a factor. Okay, so for example, if I tell you that a function has a zero of 2, then I know that the factor would be x minus 2, the opposite sign. I also know that the solution to the equation, or to the polynomial, is 2. So k is also a solution or a root of the function. And lastly, I know that 2, 0 is an x-intercept of the function. Okay, so now I'm going to use that information to help me graph a polynomial in factored form. So since it's in factored form, I don't know what the degree of this polynomial is, but I do know what the x-intercepts are. So remember, if I'm looking at x-intercepts, my y value is 0, so I just replace f of x with 0. And now I can solve this just like we have in previous lessons. So setting each factor equal to 0, I can ignore that because that's not true. I get x equals -3 and x equals 2. Notice that's being raised to a power of 2, which means we have a repeated solution here. If you remember from the previous lessons, if you have a solution that's repeating an even number of times, that's going to cause the function to bump at that point. Okay. So now I know that the x-intercepts are -3, 0 and 2, 0. And I know that at this point, we're going to bump the x-axis, and at this point, we're going to cross the x-axis. Okay, the next thing I want to do is I want to find my y-intercept. If finding the x-intercept, we needed to plug in 0 for y, or f of x. To find my y-intercept, I'm going to plug in 0 for x. So simplifying, that gives me 3. This is going to give me -2 squared, which is +4. 3 goes into that once, into this twice, to that once, to that twice, so that's 2. So our y-intercept is 0, 2. If you remember now, the last step is going to be to plug in some points. So I could plug in -1, I could plug in -2, and I could plug in +1. I'm not going to do that in this case just to save time. But what I am going to do now is consider the end behavior. So in order to find the end behavior, I need to know the degree and the leading coefficient. So this is in factored form. If I was to multiply everything out, what would be the largest power? Well, here I would get an x squared, and then multiplying it by this would give me x cubed as the largest power. So that means that the degree is 3. And if the degree is 3, I have either this picture or this picture. The leading coefficient in this case is a +1/6, so I know that this is how my graph will look. So now it's just a matter of connecting the points based on that last piece of information. And remember, we are bumping at 2, so we're going to come down, and then we're going to go back up. So that is the graph of f of x. And it's not a perfect graph, but it's just meant to be a rough sketch. Okay, moving on. You can use the location principle to help you find real zeros of polynomial functions. If f is a polynomial function and a and b are two real numbers, such that f of a is less than 0 and f of b is greater than 0, then f has at least one real zero between a and b. So basically what this is saying, breaking it down, is that if you have two x values, a and b, so if I have an x value of a here and an x value of b here, and I plug those values into my function, so plug a into the function, plug b into the function, I'm going to get corresponding y values. So this point here, I could write as a comma f of a, right? And this point here, I could write as b comma f of b. Remember, f of b is just the y value when you have an x value of b. Now, if when I do that, I see that there's a sign change, either from negative to positive, or it could be the other way around, from positive to negative, the only way I could go from a negative y value to a positive y value is if I cross the x-axis. So what that means is there has to be at least one real zero between those two x values. Excuse me. Okay, how does this look in an actual problem? Let's look at example 2. Use the table and the location principle to factor f and find all the real zeros of the function. Okay, well remember, there will be a real zero if there's a sign change in my y values. And where do I see a sign change? I see one happening here, and I see one happening here, and here. From negative to positive, from positive to negative, and again from negative to positive. So I'm going to use that information to help me factor this. Now the function, I can't factor by grouping, so I have to use the rational root theorem. So that's p over q, factors of 6, so that's 1, 2, 3, and 6, over factors of 6, 1, 2, 3, and 6. Okay, so if I were to list all the possibilities out, it would be plus or minus 1, 1/2, 1/3, 1/6, 2, 2 over 2, which is just 1, and I already have that, 2/3, 2/6, which is just 1/3, I already have that. 3 over 1, so 3, 3 over 2, I don't have yet, 3 over 6, which is 1/2, I have it already. Then 6 over 1, 6 over 2, which is 3, 6 over 3, which is 2, and 6 over 6, which is 1, so that's the last one. Okay, now based on the table, and this is the important part, I can use this information to help me factor this more efficiently. So I know that I need to have a 0 between -3 and -2, between 0 and 1, and then also between 1 and 2. Okay, so which follow or which fit into that description? I'm just going to pick one and go from there. So between 0 and 1. I feel like there's actually a lot more possibilities. So let's do between 1 and 2. Okay, numbers between 1 and 2, there's only 3/2. So that's the one I'm going to start with. And again, I'm using this part of the table to draw that conclusion. I know there has to be a 0 between 1 and 2 because I go from a negative y value to a positive y value. So I'm going to use that to factor. So I'm going to use the synthetic division with a 0 of 3/2. So 6, 5, -17, and -6. 3, 2, 1, none, so I don't need a placeholder. So bring down the 6, then 6 times 3/2 is 9, 14, that's going to be 21, it's going to be 4, that's going to be 6, and look at that, it works. Okay, so I can use this to factor f of x so that it's x minus 3/2 times x squared, 6x squared plus 14x plus 4. Okay, now I can factor that second parentheses further, and I'm going to begin by factoring on a GCF of 2. So that will become 2 times x minus 3/2 times 3x squared plus 7x plus 2. Okay, now I'm going to try to factor this further, this part here. Since the a value is not 1, it's 3, I'm going to have to use the AC method. So if you remember, I start by multiplying 3 times 2, which is 6. And I think of numbers that multiply to 6 but add to 7, so 6 and 1. So this is going to become 3x squared plus 6x plus x plus 2. And then we factor by grouping. So I'm going to pull out 3x, x plus 2, pull out a 1, x plus 2. So now it's 3x plus 1 times x plus 2. And we have to remember to bring this down. So that is the complete factored form of f of x. Okay? Now remember, we use the location principle to help us because we had so many possibilities here and a lot that weren't going to work or were that were going to be annoying to check, like 2/3, 1/6, 1/3. So we use the location principle to make kind of eliminate some of the possibilities or eliminate most of the possibilities and factor it in the most efficient way. Okay, last part of the problem says to find all the real zeros. So now that I have it factored, I'm just going to set each factor equal to 0. So that's irrelevant. This gives us 3/2. This gives us negative 1/3. And this gives us negative 2. And if you notice, if we go back to the table, what was the value between 1 and 2 here? That was our 0. Well, it was 3/2. In this case, it was just negative 2. Oh, I didn't even realize that. That probably would have been an easier way to do the problem. And then, I highlighted the wrong part of this section. I didn't even realize that. I should have highlighted this part. And then from the 0 that we have between negative 1 and 0 would be negative 1/3. I didn't even realize that I gave you that information. I probably shouldn't have put this in the table because that is a 0. So you could have just started with that. Whoops. Okay. So now another important part of polynomials is something that we call turning points, or they're more commonly known as local max and min values. So basically anytime you go from increasing to decreasing, or from decreasing to increasing, you're going to create a turning point or a local max or min. Okay? It's called a local max because there are other points on the graph that are higher than that point, but it just is like a peak when it's referring to a local max, and a valley or a dip when it's referring to a local min. So in this graph, that point would be considered a local max, and this point would be considered a local min. Okay? And that's pretty much it. It doesn't have to get too complicated. One important thing to know is that if you know the degree of a polynomial, then the function is always going to have, let's say I have a degree 4 polynomial. Then I know that there will be 4 minus 1, or 3 turning points, local maxes or mins. So you just always subtract the degree by 1. Okay. For this next part, I'm going to have to use my calculator, and I won't be able to show you guys that, but just follow along on your own calculators and then check your answers with what I have. Okay, so for this, we're going to use our calculator to graph the function, and then we're going to identify x-intercepts, the points where the local max and mins occur, and determine the intervals where the function is increasing or decreasing, positive or negative, concave up or concave down. Okay, so if you remember, you go to your calculators, go to graph, type in the function, and I'm getting a pretty good view of my function if I have the window set to standard. And if you want to add the grid line, just hit menu, view grid, then add a lined grid. Okay, so the x-intercepts I'm going to use to determine where the function is positive or negative. The local maxes and local mins are going to help me write where the function is increasing or decreasing. And then if I want to find where a function is concave up or concave down, that's actually a new thing that we're going to learn today. For that, you need to find the point of inflection, and that information we're just going to pull from our calculator. Okay, so let's do it according to the colors. So first thing is x-intercepts. If I want to find the x-intercepts using my calculator, I'm going to hit menu, analyze, and 0. And then you're going to highlight to the left and to the right of the x-intercept that you see, and your calculator should say that the x-intercept is negative 1.2, comma 0. So I can come over here, and I can graph that point. This didn't ask us to determine the y-intercept, but let's just graph it. The y-intercept is 0, 6. Okay, so now if I want to do the positive or negative intervals, actually let's get the max and min points too, just so we can draw the graph. Alright, so if I want to find the max and min points, I'm going to go menu, analyze, maximum. And that point we actually already have. That's the y-intercept. I'm also going to do menu, analyze, minimum. And I get a minimum, a local minimum of 2, 2. Okay, so let's just label that over here. We have a local max at 0, 6 and a local min at 2, 2, and that's all we have. Okay, now let's just draw this. And let's just connect the points and use our graph on the calculator to kind of make a good sketch. So something like this. Okay, now again, here we have a local max. Here we have a local min. And this is an x-intercept of negative 1.2, 0. Okay, so if I want to figure out where the function is increasing or decreasing, remember you're reading the graph from left to right, and you are just thinking about walking the graph. So I'm going to highlight it in different colors, but let's start by labeling it. So we are increasing in blue. Okay. So we're increasing here, we stop, and here. Okay, so remember we always use the x values for this part. So we're increasing from negative infinity to 0 in union with 2 to infinity. And then for decreasing, we'll use pink. So this is where we're decreasing. Kind of want a nicer shade of pink so that it's not so bright, but we'll go with it. We're decreasing from 0 to 2. Okay, I'm going to erase the highlighted sections. Now we can do positive and negative. The function is going to be positive wherever it's above the x-axis, and negative wherever it's below the x-axis. So the function is going to be positive here, and it's going to be negative here. Okay, so we're positive from negative 1.2 to infinity, and we're negative from negative infinity to negative 1.2. Okay, not too bad. Hopefully this is mostly review. Lastly, for concave up or concave down, that's where the function is concave up, meaning a U shape facing up, and then concave down is just the opposite. So if I look at the graph, where do I see that U shape? Well, concave down, I see here. Concave up, I see here. Okay, so now on your calculator, you're going to hit Menu, Analyze, and go to number 5, which is inflection. And you're going to highlight to the left and the right of that section there on your calculators. And what you should get is the 0.1, 4. So that 0.1, 4 is where we change from concave up to concave down. Right there. That is the point of inflection, POI. Okay? Which means that I'm concave down here and concave up. I used the wrong color. Concave down here and concave up here. Okay, so again, you're just using the x values. So this point is 1, 4. So I'm concave up from 1 to infinity and concave down from negative infinity to 1. Oh, and I forgot to mention the point of inflection is 1, 4. Okay, let's keep going with this next example. So hit delete a couple times on your calculator so that everything clears. Hit tab, and now let's graph this next function on our calculators. X to the 4th minus 6x cubed plus 3x squared plus 6 by 3. Okay, this one I'm going to have to adjust the view. I'm going to play with it a little bit, and I'm going to go to window settings. Seems like I need to go pretty far down in the negative direction, but I might have gone a little too far down. Maybe negative 50. Okay, so I adjusted my window viewing so that the x min is negative 5 and the x max is positive 5, and the y min is negative 50 and the y max is 25. Okay, so you're going to want to adjust your window so that you get a full view of the graph. Okay, now let's do things one at a time so that we don't get too confused. The x-intercepts, let's find those first. Okay, so again, that's menu, analyze, 0. You're going to have 4 zeros. Okay. So the first one that I get is negative 1.14, then 0.289, but I'm going to round to 2 decimal places, so 0.29, 0, then 1.82, 0, and 5.03, 0. So I'm just rounding everything to 2 decimal places. Okay, now, with that information, I'm going to go straight to doing positive and negative because the x-intercepts are what I use to describe the positive negative intervals. Okay, so the function is going to be positive at the very beginning, so from negative infinity until negative 1.14. Then it becomes negative until 0.29, at which point it becomes positive again until 1.82, where it becomes negative, until 5.03, and then it's positive for the rest of the graph. Okay, so that was positive and negative. Now I'm going to get rid of those points by hitting delete, just so that way I don't have too much going on my graph. And now I'm going to find the local maxes and mins. So again, that's menu analyze, max and min. Okay, so I have 2 local mins and 1 local max. So my local max, again rounding to 2 decimal places, is 1.11, comma 5.11, and then my 2 local mins are negative 0.57, comma negative 6.51, and 3.96, comma negative 43. Okay, so I'm just going to go straight to doing the increasing and decreasing intervals now that I have that information. Okay, so from the very beginning of the graph, I am decreasing until I get to my first local min at negative 0.57, at which point I start to increase. Sorry, I want to put 0.57, at which point I start to increase, and I stop increasing at 1.11, which is my local max, and then I start decreasing again up until 3.96, which is where I begin to increase again, and I continue that for the rest of the graph onto infinity. Okay. Last thing then is the point of inflection. So remember, that's where we change from a U shape to an upside down U shape. Okay, so if I look at my graph, all the way to the left, I see a right side up U, like a regular U shape, and then a downside U afterwards. So my first point of inflection that I'm getting is 0.18. I get 0.177, but I'm going to round it, comma, negative 1.17. And the second point of inflection I get as 2.82, comma, negative 22.3. So I have 2 points of inflection. Okay, so where am I concave up versus concave down? Well, I start being concave up, so negative infinity up to 0.18, at which point I start being concave down until 2.82, at which point I start being concave up for the rest of the graph. And that's it. Okay. Last thing. Even and odd functions. A function is even when, this is the key, f of negative x produces the same thing as f of x. What this means graphically is that the function is symmetric about the y-axis. So if I reflect the function over the y-axis, like we see here, if I reflect this piece over the y-axis, I get the other half of the graph. Okay? Now for polynomial functions, and this only works for polynomial functions, the function is even if all the powers of x are even. And again, only works for polynomial functions. This is not true of rational functions or absolute value functions. Those don't apply here. Okay, then a function is odd if f of negative x produces the same thing as negative f of x. What that means graphically is that it's symmetric about the origin. So it will look the same after you rotate it 180 degrees about the origin. And similar to what we just added up here, polynomial functions if the function is, or the function is odd if all the powers of x are odd. Okay, so is this a polynomial function? Yes. So I can apply this rule up here. Okay, what are the powers of x? 3 and 1. So since they're both odd, this is an odd function, which means it's symmetric about the origin. Moving on. Is this a polynomial function? Yes. What are the powers of x? 4, 2, and anytime there's a constant function, that means I'm multiplying by x to the 0. Those are all even powers, so this is an even function. Okay, next. Is this a polynomial? Yes. So what are the powers of x? 3 and 0. Well, that's an odd and an even power, so this is neither. Okay, now, just to show you also how it works with the rules of f of negative x time and negative f of x, this is an odd function, which means f of negative x will produce the same thing as negative f of x. So what is f of negative x? Well, that's negative x cubed minus 7 times negative x. What is negative f of x? That's negative x cubed minus 7x. And the question is, are these two things equal? If they are, it's an odd function. Well, negative x cubed is negative x cubed. Negative 7x times negative x is positive 7x. Distributing the negative on the right, I end up getting the same thing. Okay? And then you do the same thing for these as another way to check. And that's the end of the lesson.